Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is continuing our Composites playlist, and today we're going to look at test methods for composites. Let's see how it works. So there are a number of ASTM standards for evaluating composite structures. For example, three-point bending is governed by ASTM 393, three-point bending for sandwich structures. It defines both three-point bending and four-point bending samples. Four-point bending is better because when you have three-point bending, you get your shear, which is constant across the beam, flipping, and your moment is building up from the edge to the point of application. So your max moment occurs right where you're pressing on the structure. And so if you have a defect somewhere else, really it's only testing that middlemost piece, and you're going to get fairly significant deflection right where that load is applied. It's not really ideal, but it's simple and quick and can give you decent numbers for certain kinds of things, shear and things. If you have four-point bending, what that does is now you have shear is constant from the outer support to the inner support, and then, or the inner load application points, and then you have no shear between the two attachments where your load is applied, your center to a point, load application points. What that means is you've got a constant, your moment builds up from 0 to the max value, then it's constant all through. What that means is you're getting a more uniform loading on the compressive fascia, which is usually the critical one. And so any defects in that region are going to be more representative of the global structure. You have constant moment, so there's less chance of your load application messing up or tweaking your results. So a four-point bend is a better approach for getting like face sheet allowables and things like this. So this is generally used for evaluating the face sheet allowables for sandwich in bending, and it's sometimes used as a conservative estimate of the compression allowables of the sandwich, although it obviously won't pick up shear crimping. The next standard is ASTM 273, which loads like this and can be used for shear properties of the sandwich. Also, we have flatwise compression. ASTM 365 governs that. There's you can also get C327250 is another one that defines flexural and shear properties for sandwich kind of structures. And we're doing sandwich compression, and you want to look at that compression loading. They've got ASTM 5467, which also gives details of how that can be done, although our first one can also be used for that. If we're looking at polymer matrix composites like fiber reinforced composites and things, this is a typical set of samples that you can use, and the ASTM calls out a number of different types of samples that are acceptable and dimensions for those samples. You'll notice they have nice basically, they're long enough so you can grab them with the grips. They have a nice, even distribution of material so that your stress riser is not too much, and they've got a long enough grip length, a long enough point where you can evaluate the loading with no tweaks from where the grips are applied in order to get good data and maybe fit an extensometer in there. So for tension testing, these are pretty good. It lists out a bunch of different methods you can use. Another tension ASTM is D3039, which calls out another kind of sample. You notice those first samples for ASTM D638 has a single piece of material. So you build up a little composite sandwich, you cut it into the shape, you're careful with your cutting to get no stress risers, and it's all right there in that one sample. With these samples, these are easy because you can just cut it straight samples, and then you post bond on grips, top and bottom, which then, so if you have just a flat panel and you bond on the grips, you don't have to machine, you have easier machining, you just have your extra pieces bonded on. And once again, those are designed so that the grip is not where you fail, to have as near zero stress riser as you move into the sample. And once again, your center section is set so that you can fit a extensometer and that kind of thing. So, and then another common one, I'll put this one on edge, is this hole standard ASTM D5766, which can also be used when you have a hole in the sample and you want to evaluate that. There's actually, the ASTM also provides a guide for composites with a myriad of different tests. These are just some of the more common ones, and there are other ASTM standards for various idiosyncrasy kind of tests. You can look through this document and look at the different ones that are recommended. The most important thing when you're testing is to evaluate something that's representative of your structure and that you can get enough samples to have a reasonable A and B basis allowable, so that not so many that you're just spending money frivolously, but so that you get enough so you can get a nice A and B basis allowable. Now, if you're trying to develop properties for MMPDS or something, you're going to generally be required to have more samples to go and put these out publicly as the allowables for a certain type of material, and then your batches and everything have to be carefully controlled and all this. But for much engineering work, especially as you get closer to the edge of what we understand, so you get out into more rockets and satellites, you tend to be working more on the fringes of knowledge. The important thing is to come up with a simple test that characterizes your material, that you can evaluate the critical failure modes, have a reasonable number of samples. 7 to 15 is a good number. 15 if you got a little more budget. 7 samples generally is sufficient for many simple tests to give yourself a reasonable B basis allowable. If you're doing testing for materials that are going to be used more widely, you're probably going to want more samples. But if you're just saying, hey, look, I got this little problem, I got this little issue, I want to make sure that I've got enough peel strength, or I want to know that this little defect has been quantified, or I have this thing that is flying everywhere, but I want my own verification testing, then a smaller number of samples, maybe 7-ish samples to 15-ish samples, is generally, in my opinion, sufficient to get enough confidence to move forward. If we are loading our composite samples in shear, you can use a 3-point bend test. In-plane loading is governed by this ASTM. There's also an ASTM for shear that uses shear of notched samples, and also a double lap shear one. Once again, these are just a few of the more common ASTMs, and there's a myriad of those out there for little idiosyncrasies of characterizing material strengths. For bearing, this ASTM will cover that. And for compression, we'll use a short compression often. This is a shaped sample I have used in the past, where we'd go, and especially when we're doing characterizing defects, we would go cut little samples out of the area that was shown by the OS, the ultrasound, to be good material or to meet expectations or requirements. And then out of the material that was defect, we'd cut little flat samples. We'd bond on our little grips onto them, and then with a really short test sample, because when you load in compression, any kind of thin sample is going to tend to buckle, and you want your compression allowable to actually give you a compression allowable and not a buckling allowable. So these have to be super short in order to, and obviously for a 1.5-inch long grip test region, you're going to have a pretty thick sample to not get a buckling kind of failure. If you're doing adhesives, this ASTM is one of many that can give you lap shear strength and this kind of thing. So let's go ahead and let's talk about, all right, so those ASTMs are cool. And if you're actually testing, you're going to want to pull those up and follow those. But let's say you're trying to characterize your own testing and you're looking through the ASTM and go, oh my gosh, there's so much material here. Let's just kind of summarize the basic needs to characterize simple properties. And I'm going to drop a few figures from some of the ASTMs as we go through here. And I think I'm pulling most of those figures from Jones' books. although these are the same figures that are in the ASTMs for the most part. So if we want to characterize, let's say we have a composite laminate and we want to characterize its capability. What you're going to do is we're going to need our modulus values, material directions in the primary material direction, the principal material directions 1 and 2. And we're going to need our Poisson's ratios, we're going to need our shear strength, and we're going to need some allowables. So what we can do before testing, we need to understand, okay, what material are we trying to quantify? What kind of variation do we get between the materials? Are we talking do we always have like a 5-ply or a 4-ply graphite epoxy, or do we have doublers in places? Do we have LTM in places, low temperature cure stuff? Do we have thicker doubled areas in places? Or do we have changes in thickness? You may need to characterize all of these, or with clever engineering, you may be able to bracket these and say, well, I'm going to test this, this, and this, which should be critical. These two samples are going to tell me not only what the allowables are for a certain thickness, but the allowables are for another thickness, and use analysis to show, well, because we have this and we've characterized it like this and we've analyzed between that, we may be able to quantify other ones in between. So we need to understand, what is the purpose of our test? We need to visualize, how is that going to fail? How are the loads introduced into the structure itself? What are the peak loads that we're seeing? Are we looking for representing our loads and just qualifying our structure by this test? Or are we trying to get a set of decent allowables that can be used for a wider range of things? We also, when we make our test setups, it's very common to make decisions to save money that end up not characterizing appropriate. It looks like it characterizes the major failure modes, but then we introduce some other failure mode that maybe we didn't perceive by the test fixture being too rigid or too soft, or not loading it correctly, or having eccentricities that we didn't account for. These kind of things can waste a lot of money and cause dangerous failures at times. We want to think about what can go wrong with this testing. Have we, in terms of the different batches of material, where we're getting our fiber, where we're getting our prepreg, where we're getting our matrix material, if we're building that up separately, what sources do we have this material, and what is the variation between the various batches? All these things kind of need to be figured out. But let's keep on trying to come up with just a way to characterize this. So here is a typical sample. This is a picture from Jones, but it's one of the ASTM figures. We can see we've got our loading region where we're gripping the thing. You're going to generally need to make this bigger where you're grabbing it. So we can do this by machining that material wider, like we talked about before, or by keeping a straight sample and attaching bonding on grips to it. Okay, and either of those need to slowly taper into the area that we're actually evaluating the test, so that we don't introduce stress risers that'll skew our results. You're going to have that transition region, which is designed to eliminate the stress concentration factor, and then you're going to have the gauge region. And typically we're going to expect the sample to fail somewhere in the middle of the gauge region. We're going to figure it's a good test. If it fails right near the change in geometry, then we're going to be suspect of that. That doesn't mean that failure is not valid, but it means that it might not be valid. It might have failed at an early point because of stress risers from the grips. So you want to watch if there's any failures occurring closer to the change in geometry. You're going to want to be a little suspicious of those to figure out whether that was influenced by that. Okay. You also may need to evaluate environments with graphite epoxy and various composites. Some of them are susceptible to moisture ingress, and that moisture typically lowers properties, especially at higher temperature and sometimes at colder temperatures. And so if your material in your application can be exposed to temperature or moisture, then you're going to need to account for that. But temperature is fairly easy to account for, because you can either put it in an oven or you can use heat lamps with thermocouples to evaluate the temperature of the material. If But if it's moisture, you may need to first condition the material, estimate some faster way to introduce the environment, because usually we can't wait for months and months and months or years and years while we develop the moisture content that simulates reality. So we'll put it in a chamber that will accelerate that process down to a few weeks to a couple months. And then once you've determined that, you're going to want both dry allowables and wet allowables if it can get wet. And then we're looking for a sample kind of like this. So we talked about these three regions. The gauge region is generally set once again so that an extensometer, like a 1 inch or a extensometer, can evaluate the change in deflection. For a lot of properties, we'll use load head deflection for when we're just looking for strength. But if you want to get any kind of modulus or stiffness, you're going to need a strain gauge in order to get a more accurate value. It's very difficult to get a good modulus value because the slop in the machines often can cause enough softness that your slope is not really a proper reflection of what the true modulus of the material is. So we talked about this kind of sample. We're going to fabricate our samples. We're going to make sure they're free of flaws and inspect them to ensure that. Often with composites, we have to be careful how we cut them because it's easy to get, because your composite sample is typically a lot narrower than your actual structure, which is a lot more continuous. A lot of times the composite structures are rather wide and long, and the cut effects are over near the edge at a point where often it's thickened up and less critical. When you have these samples, they're a lot smaller, so any kind of issue from cutting the sample can adversely affect your results. So you want to cut carefully with the right kind of saw, the right kind of blade. If we have a wet sample, a lot of times we're going to try not to drive off that moisture, and so what we'll do is cut it wet with a wet saw so that it doesn't drive off the moisture. Also, a lot of times we'll have someone sand or polish the edges of the sample so you don't get any stress risers from the cut edge. So you're going to want to make sure these things are basically pristine samples that are reflective of the materials that you're testing, but you haven't introduced any flaws based on the dimensions of your sample or the way it was fabricated or cut. You then are going to evaluate once you've designed your gauge region. Now, if you're following the ASTMs, that's a little easier. Just follow one of the appropriate ASTMs. If you're doing your own testing and flying by the seat of your pants, so to speak, it's a lot harder because there are a lot of things that you may not think about that can influence your results. By following the ASTMs, you're going to tend to get someone else with a little more experience driving some of the decisions, like load head speed. A lot of engineers would be like, well, what speed do I even want to test this at? I remember the first time I was asked, hey, what speed do you want to test this at? I'm like, I don't know. Because the guy that was doing the testing had he wasn't an engineer, but he had a lot of test experience. He goes, well, the ASTM say blah, blah, blah. I said, let's do that. And that ended up working pretty good for us. As you do more testing, if you do a lot of testing, you'll start getting a feel for what load speeds are representative and will allow both that the machine can maintain and also that will not introduce issues with your testing. So once you've designed your sample, thought about how it's going to perform, we then are going to go ahead, cut our samples, measure them carefully, identify them so that the measurements and the results all are identified back to the sample so you can inspect the sample afterwards. You're typically going to want an extensometer or some kind of load indicator. I usually like to have a load deflection curve coming straight out of the machine, plus have strain data so that we can verify that as well. Okay, so once again, we talked a little bit about the different styles from the different ASTMs. This is one style we kind of talked about coming out of the D638 ASTM. This is the type 1 sample, and there's guidance in the ASTM for what size sample is more appropriate for certain kinds of things. Here's a different style out of another ASTM and another style. We saw some of these before with the ASTM pictures, and these are Jones's pictures for these. This one, sometimes called a bow tie sample, you'll notice that it's a lot softer. It's more carefully designed. This can be harder to make well, and you've got such a long region, but this will do a better job of eliminating the stress risers. You'll notice because this is loaded, instead of grabbing it with grips, you'll notice it's got holes to load with a punched through element. So now you got to be careful for bearing and tear out failures at the edge, which means it's going to probably have to be either a lot wider or a lot thicker out here at the edges for that kind of sample. So let's go ahead and move forward. Let's say, okay, so we've chosen our test sample, we've made our tension samples, we've chosen what ASTM we're going to follow, what our sample is going to look like. Our set number 1, we're going to need samples where we make samples where we can make a big, let's say we're testing unidirectional material. We make a big old panel of oriented in one direction. Now we can cut a bunch of samples loaded in that direction where the samples are in the longitudinal direction. We can cut a bunch of samples in the 2 direction. So now we've got our 2 direction samples, and we can cut a bunch of samples in the 45 degree direction. So now we've got, from the same panel, we can cut samples that are 0 degree, 90 degree, and 45 degree. And typically this will be sufficient to give you the properties you need to characterize your composite material. So you've got your 0. Now, if you're using a woven fabric that's allegedly has the same properties in 2 dimensions, you might end up deciding you're just going to test one direction. However, it's a good idea to still have 0, 90, and 45 samples, because the 0 and the 90 will identify whether you truly have the same. A lot of times the fill direction is not quite as strong or stiff as the warp direction, and that can verify that for you. So let's say that we've made our samples, we've made our panel, we've cut out our 0 degree, our 90 degree samples, and our 45 degree samples. We're going to take our 0 degree samples, we're going to load them in our machine, we're going to measure both the loading so we can calculate stress and the strain. Ideally we'll have a strain gauge in there, and we can measure the strain in both directions, in the 1 direction, the 2 direction, so we can get Poisson's ratio effects. So we're going to need a strain gauge in the longitudinal direction, a strain gauge in the 2 direction. We can now calculate from this, we can calculate our E1 from this stress strain curve. We can determine our Poisson's ratio 1:2 as the ratio of those strains, and we can calculate our ultimate strength, tensile strength, from that in the 1 direction. We now take our second set of samples, which are loaded at 90 degrees. Now we're testing perpendicular to that, and we're going to do the same thing. This will give us our E2, and now we'll get our Poisson's ratio in the 2:1 direction, and we can verify that it's roughly satisfying this relation V2:1, or Poisson's ratio 2:1, is equal to 1:2 times that ratio of the moduli. It should match that fairly well. Sometimes tweaks in testing can cause that to not perfectly match, and then we can get our strength in the 2 direction. Okay, after all this, we're missing our 45 degrees, so now we're going to take our 45 degree samples and we're going to test those to failure as well. We're going to once again plot our load deflection. We're going to have strain gauges on this. We can measure the strain in the loading direction, which we're calling the X direction, the body coordinates, right? And then remember, we can now calculate our approximate E is whatever E we get in that direction. That's our EX. Remember our equation for getting the equivalent E at some off angle? Well, actually, we're testing to get to exactly that value. So whatever our stress is, our P over A stress divided by whatever strain in that 45 degree direction, that will tell us our modulus in that 45 degree direction. Now, recalling our equation for equivalent modulus, which I've shown you here, we now can rearrange that to calculate the shear modulus. So we're not actually calculating EX, we're calculating EX by P over A over the Poisson's ratio in that 45 degree direction. And then we're using that with the E1 and the E2 that we just got from our other 2 tests, and our Poisson's ratio 1:2, we plug into this equation for G12, and now we've got a reasonable estimate of G12. And ASTM D3518 recommends we can calculate our shear strength, which F12, which we also call F6, as just that force over the area, twice the area. Now, if you want compression strength, you're going to need those short samples. I actually like those little short ones with grips that we looked at, we talked about before. And I've got some pictures of those. I've got some of those hanging in my office. But anyway, so we would, once again, we'd load this up. You need to first evaluate it analytically to make sure it's not going to buckle. And then you're going to have to watch that test carefully. You may even want a deflection gauge out of plane to make sure it's not, you're not getting a buckling failure, you're actually getting a compression failure of the fibers. So you can load your samples in there, evaluate your E1, your Poisson's ratio, and your compressive strength for the material. Remember, this test is a compressive stress. If it's a representative sample, that means that will capture the compressive strength, whether it happens to be ultimate or one of those stability modes that are within the matrix based on the layup. This will pick that up. What we want to make sure it doesn't do is go into an Euler buckling kind of failure, because that we can do analytically, or we want to make a longer sample to evaluate that. If we're trying to get F1C, we need this to be short enough so we are picking up those stability failures that are within the composite, but not the ones that are a function of our geometry so much. Okay. So that is how we do testing of composites. You're going to want to get a hold of those ASTMs to kind of read through those. You can find there's a lot of material, but I have here make it a little easier to kind of get your feel for what it is you're trying to do, and then go with the STM to get the precise dimensions and load rates and equations for your particular application. Hope this helps. Enjoy.